Howdy Pre-Cal. We are now delving into chapter 12. If you had me for Algebra 2 last year, then what we're going to cover in chapter 12 will be a lot of review of what we did at the very end of the year. We're going to be dealing with sequences and series in this chapter, and that's what we did at the end of last year in Algebra 2. So we're going to start off today talking about sequences and what we call summation notation. So it says a sequence is a list of numbers written in a specific order. This week, as we get into talking about sequences, and you might remember this from last year in Algebra 2, but there are several different types of sequences. We will talk about the arithmetic sequence. We'll also talk about the geometric sequence. But really just a sequence is just a list of numbers written in a specific order. A series is what one gets by adding those numbers in a sequence together. So here, this is what a sequence would look like. A sub 1 is the first term, A sub 2 is the second term. If you're wondering what I'm saying A and then sub, S-U-B, and then 1. And the reason I'm saying sub is because 1 is called a subscript. Anytime you have that little tiny number or letter down there that's written at the bottom. And so when the exponent's at the top, we call that a superscript. I don't know if you knew that. Well, these, when they're at the bottom, they're called a subscript. So this is a sub 1, this is a sub 2, this is a sub n. So if you're wondering what in the world is she saying, that's what I'm saying. And that little number lets you know what term you're looking for. So that represents the first term, like A sub 4 represents the fourth term in the sequence. All right, then it says a sequence is a function whose domain is the set of natural numbers. You may have forgotten, sorry, I feel like I'm gonna sneeze. Whew. You may have forgotten what natural numbers are. Natural numbers start with 1, and then they go to 2, 3, 4, 5, 6. And on and on and on. They don't include 0, they don't include negatives, they don't include fractions, they don't include decimals. So 1, 2, 3, 4, 5, 6, ... That's what natural numbers are. In case you forgot that, I'll just write that on here. Okay. All right, so let me go back and read this again. A sequence is a function whose domain is the set of natural numbers. The values of f of 1, f of 2, f of 3 are called the terms of the sequence. So for example, 2, 4, 6, 8, 10, those are the terms of the sequence. The first term, the second term, the third term, the fourth term, the fifth term, and so on. It says, while this sequence consists of even numbers, we need to specify a formula, otherwise known as an equation, for finding all of the terms of the sequence. This can be done by giving a formula for the nth term, which we call a sub n, of the sequence. So for this particular sequence, since it's even numbers, it would be a sub n is equal to 2 times n. Now what does n represent? Well, remember we said that n represents the number of the term that you want. That's otherwise known as the domain. So if I want the fourth term, then n is 4. If I want the 20th term, then n is 20. So that n represents the domain. Where is it in line of the values? It says, remember, domain is the input variable. It's kind of like what we normally use as x, right? The domain is what you're plugging into your function. All right, so example number 1 says to find the first 5 terms and then to find the 100th term of the sequence defined by each formula. So basically they're telling you for n, we're gonna plug in 1, 2, 3, 4, 5 because we want the first 5 terms, and then we're also going to plug in 100 because we want the 100th term. So let's start with letter A. We're gonna find a sub 1, so we're gonna plug in a 1, and 2 times 1 is 2, and 2 minus 1 is 1. Now let's find the second term. So we're gonna do 2 times 2 minus 1. 2 times 2 is 4, 4 minus 1 is 3. Now let's find the third term. 2 times 3 is 6, 6 minus 1 is 5. You might notice a pattern here. Anybody? 2 times 4 is 8. 8 minus 1 is 7. What do you guys think the next one is? I am going to guess that the next one is going to be 9. Am I right? 2 times 5 is 10. 10 minus 1 is 9. I am right. All right, 100th term. Anybody, can we guess that one? 2 times 100, or yeah, 2 times 100 is 200. Minus 1 is 199. So we found the first 5 terms and the 100th term. All right, letter B. We're going to do the same thing. So I'm going to plug in a 1. 1 squared is 1. 1 minus 1 is 0. Second term. 2 squared is 4. 4 minus 1 is 3. Third term. 3 squared is 9. 9 minus 1 is 8. Fourth term. 4 squared is 16. 16 minus 1 is 15. Fifth term. 5 squared is 25. 25 minus 1 is 24. And now the 100th term. 100 times 100 is 10,000, and 10,000 minus 1 is 9,999. Yeah, I wouldn't have guessed that. Okay, next one, letter C. Here we go. First term. We're going to have 1 over 1 plus 1, which is 1 over 2. Second term. We're going to have 2 over 2 plus 1, which is 2 over 3. Third term. 3 over 3 plus 1, which is 3/4. Fourth term. 4 over 4 plus 1 is 4/5. Fifth term. 5 over 5 plus 1 is 5/6. And lastly, man, my hand hurts. It's like carpal tunnel. The 100th term, we're going to have 100 over 100 plus 1, and we get 100 over 101. See, these aren't too bad. Maybe a little tedious, but they're fairly easy. All right, letter D, first term. We're going to have -1 to the first power over 2 to the first power. -1 to the first power is -1. 2 to the first power is 2. All right, second term. -1 to the second power is +1, and 2 to the second power is 4. Third term. -1 to the third power is -1. 2 to the third power is 8, so we get -1/8. Fourth term. -1 to the fourth power is 1. 2 to the fourth power is 16. All right, fifth term. -1 to the fifth power is -1. 2 to the fifth power is 32. And now for the 100th term. All right, -1 to the 100th power. Well, if you look at the pattern, so if you struggle with that, if you're looking at the pattern, when you raise those numbers to odd exponents, you're getting a -1 every time. When you raise it to an even exponent, it turns it into a +1. So what's going to happen with ours is going to turn it into a +1. 2 to the 100th, I am just going to leave it as 2 to the 100 because I suspect that that number is so large that the calculator, see, look at that. It gives me the number in scientific notation because that number is just huge. So we are just going to leave it. So we have 1 over 2 to the 100th power for the 100th term. Okay, example 2. It says find the nth term of a sequence whose first several terms are given. Here's where you really have to put your thinking cap on. So this first term is 1/2. It's the first term, so that means it occurs when n is 1, when the domain is 1. Then the second term has an n value of 2. The third term has an n value of 3. The fourth term has an n value of 4. Why is that important? Because as you're writing an equation, you need to be thinking about what n is, because everything is going to be in terms of n. I need a to the nth power equals what? How am I going to relate this to n? Well, why don't we look at the denominators first? This is 2, 4, 6, 8. Those are even numbers, right? So how could I get this? Well, if n is 1 and I got a 2, could I do 2 times n? Yeah. Would 2n work for this one? 2 times 2? Yep. Would 2n work for this one? Yep. 2 times 3. Would 2n work for this one? Yes, 2 times 4. So my denominator is going to be 2 times n. What do you notice about the numerators? They're odd numbers. Not only are they odd numbers, but all of the numerators are exactly 1 less than whatever their denominator is. 1 is 1 less than 2. 3 is 1 less than 4. 5 is 1 less than 6. 7 is 1 less than 8. So if I already know what the denominator is, which is 2n, and I subtract 1 from it, that will give us the numerator. So this would be the equation for the nth term. Now sometimes we don't come up with them very quickly, and you have to do a guess and check method where you guess something and you see if it works. And if it works, good for you, like this one worked out nicely. If it doesn't work, you try again. That's okay. Some people get them quickly, some people it takes them a little bit longer, but the idea is if you practice, you begin to get better. So let's take a look at the next one. Now notice that the -2, that is when n is 1. The 4 is when n is 2. The -8 is when n is 3. The 16 is when n is 4. And the -32 is when n is 5. I'm really hoping you notice something here. Anybody notice? Ignore the signs for a minute. Just pretend you have 2, 4, 6, 8. Or I'm sorry, no 6. 2, 4, 8, 16, 32. Well, how could you get a 2? 2 to the first power. How could you get a 4? 2 to the second power. How could you get an 8? 2 to the third power. 16 would be 2 to the fourth power. 32 would be 2 to the fifth power. So 2 to the first, to the second, to the third, to the fourth, to the fifth. So 2 to the n power. Now this would not be the final answer though, because all of those things I said would give you positive answers, and we don't have all positive answers. We also don't have all negative answers, but earlier we saw that when you have a negative number and you raise it to an odd exponent, you get a negative, but when you raise it to an even exponent, you get a positive. Same thing would be happening here. So what if we make that a -2 and put it in parentheses? Would this work? Let's try it. -2 to the first power would be -2. -2 to the second power, there it would turn into a positive, right? -2 times -2 would be +4. -2 to the third power would absolutely be -8. So it looks like this will work. All right, some sequences don't have simple defining formulas. Basically, the ones we did, they're telling us are pretty simple so far. The nth term of a sequence may depend on some or all of the terms preceding, that means that come before it. So in other words, you may need to know previous terms before you can find what you're looking for. So maybe if I wanted the 6th term, maybe I need to know the 5th term to find it. Or maybe if I want the 25th term, I need to know the 24th term to find it. And if that's the case, then that is called using, it's a sequence defined in what we use the word recursive, meaning you have to know what's in front of it before you can find what you're looking for. So it says find the first 5 terms of the sequence defined recursively by a sub 1 equals 1 and a sub n equals this guy right here. They're pretty much already telling you the first term is 1. Now's where we're going to use the formula. So now we want to find the second term. That means that n is 2. So according to this formula, we're going to have 3 times a to the 2 minus 1, that's my subscript, plus 2. All right, let's talk about that. What would 2 minus 1 turn into? It turns into 1. So here's what we know. To find the second term, I need to know the first term, that's why they gave it to us, and then I'm going to take that first term, add it to 2, and then multiply by 3. So 1 plus 2 is 3, and 3 times 3 is 9. So we now know the second term. All right, let's see what happens when we want to find the third term. So in other words, this time n is 3. So according to this formula, I have 3 times a sub 3 minus 1 plus 2. That means that I need to know the second term to find the third term. So we just found out that the second term is 9, so we're going to plug it in. Then we have to do 9 plus 2, which is 11, and 11 times 3 is 33. Here's the danger with recursive formulas, and this is why you have to be so careful. If you mess up finding the second term, you're going to now screw up the third, the fourth, the fifth, and however many other ones you're looking for. So you want to make sure that you're paying attention to your math, pay attention to the details, and don't mess up, because if you mess up early on, it messes up everything behind it. All right, now we're looking for the fourth term. That means that n is 4. And so according to our recursive formula, that means we need to know the third term in order to find the fourth. Well, we just found out the third term is 33. 33 plus 2 is 35, and 3 times 35 is 105. One more to go. Now we're going to do the fifth term. That means n is 5. So I'm plugging in a 5 for the n, and that means I need to know the fourth term so that I can find the fifth. We just found out that the fourth term is 105. 105 plus 2, that would be a whopping 107, and 107 times 3 is 321. So now we have the first 5 terms of the sequence. So you have to be careful with the math there. You don't want to make little mistakes because it could mess you up later on. All right, example 4 says find the first 11 terms of the sequence defined recursively by this. They give us the first term, they give us the second term, and then they give us a recursive formula to find the rest. This is actually called the Fibonacci sequence, and I'm so sad we're not together as a class because I do a really cool activity with the Fibonacci sequence. So maybe ask me about it one day. Okay, so here we go. We're going to find 11 terms. Are y'all ready? Here we go. So the first term is 1, and the second term is 1. All right, let's try for the third. That means n is 3. So let's look at what that means. That means we need f sub 3 minus 1 plus f sub 3 minus 2. What does that mean? That means that we need the second term and the first term, and we're going to add them together. So both of those are 1, so we get a 2. So basically what this formula is telling us is whatever term you need the 2 in front of it to add together. So far we have 1, we have another 1, we have 2. Let's try for the fourth. So again, n is 4. So I'm plugging in a 4 for the n. That means I need term number 3 plus term number 2. Well, we just found out that term 3 is 2, and we were given that term 2 is 1, and this means that our fourth term is 3. All right, rather than writing all of this out, because I feel like we can do it, the formula tells you whatever you need the 2 in front of it to add together. Okay, so we want the fifth term next. That means we have to add the fourth and the third. So 3 plus 2 is 5. Now we have the fifth term. Now we want the sixth term. That means we need the fifth and the fourth, and we're going to add those together, and we're going to get 8. Now we want the seventh term. So we need the sixth and the fifth, and we're going to add those together, and we're going to get 13. Now we want the eighth term. So we need the seventh and the sixth. We're going to add them together. We're going to get 21. I forgot what number we're on. I think we're on number 9. That means I need these two, and we're going to get 34. Then I need number 10, so we're going to add these two, and we're going to get 55. And then number 11, we're going to add these two, and we're going to get 89. So the Fibonacci sequence says whichever term you're looking for, you have to add the 2 in front of it together. Okay. Here it says in calculus, we're often interested in adding terms of a sequence. We have what are called partial sums of a sequence. So it says if you have this sequence, again, you have first term, second term, third term, going up to the nth term, partial sums, S sub 1 tells you you want to add just the first term, which means there's just that first term, that's it. S sub 2 means you want term number 1 and term number 2, and you're going to add them together. Why are they using S? S is for sum. S sub 3 means take the first, second, and third terms and add them together. So N is going to tell you how many of the terms you're going to be adding together. So let's take a look at example number 5. It says find the first 4 partial sums. That means we're going to find S sub 1, S sub 2, S sub 3, S sub 4, and the nth partial sum. So our goal, we're going to find S sub 1, S sub 2, S sub 3, S sub 4, and S sub n. And they gave us this formula so that we could find the terms. Does that make sense? So the first thing we're going to do is just find the first 4 terms because we're going to need those. So I'm going to go all the way over here. So A sub 1, that's 1 over 2 to the first power, which is a half. A sub 2, that's 1 over 2 to the second power, so that's a fourth. A sub 3, that's 1 over 2 to the third power, that's 1/8. And A sub 4 is 1 over 2 to the fourth power, and that is 1/16. Now that doesn't answer the question, that just gives us what the first 4 terms are. So let's start with S sub 1. That means you just have the first term. There's nothing to add to it because you just have one term. So we're done with that one. S sub 2, we're going to add the first and the second term together, but I need a common denominator. So 1/2 turns into 2/4, and 2/4 plus 1/4 is 3/4. S sub 3, we're going to add the first 3 terms together. We need a common denominator. 1/2 turns into 4/8, 1/4 turns into 2/8, 1/8 stays as 1/8, and 4/8 plus 2/8 plus 1/8 is 7/8. S sub 4, term number 1 plus term number 2 plus term number 3 plus term number 4. We need a common denominator, so 1/2 turns into 8 over 16, 1/4 turns into 4 over 16, 1/8 turns into 2 over 16, and 1/16 remains the same. 8/16, 4/16, 2/16, and 1/16 all add up to be 15 over 16. So we found the first 4 partial sums, but now we have to find the nth partial sum. And again, this is where you got to put on your thinking cap a little bit. Okay, so let's look at all of these sums. Here was when n was 1. This one was when n was 2. This one was when n was 3. This one was when n was 4. I would say maybe let's start by looking at the denominator. 2, 4, 8, 16. Seems like we saw those in an earlier example. We kind of see them over here too, don't we? 2, 4, 8, 16. Where did those numbers come from? 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So we will say 2 to the nth power, right? Okay, let's look at the numerators. What do you notice? 1, 3, 7, and 15. No major pattern there, but what I can tell you is that 1 is smaller than 2 by 1. 3 is smaller than 4 by 1. 7 is smaller than 8 by 1. And 15 is smaller than 16 by 1. So if I know how to get the denominator, all I need to do is subtract 1 from it, and that will give us the numerator. And so that is the nth partial sum. Ta-da! All right. Woo. We're gonna do the same thing for this next one. Is everybody excited? I can feel the excitement from where I am. Okay, first term. So using the formula, we're gonna do 1 over 1 minus 1 over 1 plus 1. So that is 1 minus 1/2, which is a half. All right, second term. We're going to do 1 over 2 minus 1 over 2 plus 1. So we have 1/2 minus 1/3. Need common denominators. So that's going to be 3 over 6 minus 2 over 6, which is a whopping 1 over 6. All right, third one. We're going to do 1/3 minus 1 over 3 plus 1. So we have 1/3 minus 1/4. Is it raining outside? It is. Sorry. That's my squirrel moment. I need a common denominator. That's going to be 12. So I got 4/12 minus 3/12, which is 1/12. One more to go. We're going to have 1/4 minus 1 over 4 plus 1. So that's 1/4 minus 1/5. Need a common denominator, 20. So that's going to be 5 over 20 minus 4 over 20 with an answer of 1 over 20. So far, we know the first 4 terms. Okay, partial sums. So S sub 1 is just the first term. I like that one. All right, S sub 2, we're going to take the first 2 terms, add them together. Need a common denominator, so 1/2 turns into 3/6. 3/6 plus 1/6 is 4/6, which reduces to 2/3. All right, third sum, we're going to take 1/2 and 1/6 and 1/12 and add them together. 1/2 turns into 6/12. 1/6 turns into 2/12. 1/12 remains the same. If we add those together, we get 9/12, which reduces to 3/4. All right, fourth one, we're going to do a 1/2 plus a 1/6 plus a 1/12 plus a 1/20. All right, common denominator. Let's see. Not 20. 60 would work. Whew. Okay, so 1/2 turns into 30 over 60. 1/6 turns into 5 over 30. No, just kidding. 30 is not my denominator. That was silly. Okay, 10 over 60. Now we're talking. 1/12 turns into 5 over 60. And then 1/20 turns into 3 over 60. All right, so now let's add those together. 30 plus 10 is 40. 40 plus 5 is 45. 45 plus 3 is 48. We get 48 over 60. Both of those numbers are divisible by 12, and that turns into 4/5. You might have noticed a pattern here, did y'all? So this first sum was when n is 1. This second one is when n is 2, and then the next one n is 3, and then the last one n is 4. So we now want to come up with the nth sum. Well, look at n being 1 and the answer. And when n is 2 and that answer. And when n is 3 and its answer. And when n is 4 and its answer. What do you notice? Well, I notice that the numerator is always the same thing as n. When n is 1, my numerator is 1. When n is 2, the numerator is 2. Same thing happens for 3, same thing happens for 4. So the numerator is always going to be n. What do you notice about the denominator? Here we have a denominator of 2. How is it related to n? It's 1 bigger. The next one we have a denominator of 3. How is it related to n? It's 1 bigger. You might be following here. 4 is 1 bigger than 3. 5 is 1 bigger than 4. So the denominator is always 1 bigger than the numerator. Boom, got it. Okay, so last thing that we have here. This is where we get into what we call sigma notation. We definitely did this in Algebra 2. So it says, given a sequence, we can write the sum of the first n terms using summation notation. Again, fancy word for you're adding. Also known as sigma notation. And the reason we call it sigma notation is because we're using the Greek symbol sigma. That's that guy right there. That's the Greek symbol for sigma. Okay, so when you see this symbol, sigma notation, also summation notation, it means you're going to be adding terms because it's a sum. That's the key phrase right there. We're going to be adding. Here it says that you're going to start when k is 1. So in other words, with the first term, whatever is down here. So if that were a 5, we would start with the 5th term. If that were a 22, we would start with the 22nd term. Whatever is down there tells you which term you're going to start with, and then the number at the top tells you which term you're going to end with. So the bottom number tells you where you're going to start. The top number tells you where you're going to stop or end. So the way that we would read this out loud, we would say the sum, because there's that symbol, the sum of a sub k from k equals 1 to k equals n. That's how you would read this part right there. Okay? Let's apply it. So this first one says find each sum. So this is your formula. This is your equation, k squared. We're going to start when k is 1. We're going to end when k is 5. So when k is 1, we would have 1 squared. When k is 2, we would have 2 squared. When k is 3, we would have 3 squared. When k is 4, we would have 4 squared. When k is 5, we have 5 squared, and that's when we stop. So we started here when k was 1, we end here when k is 5, and we're adding because this is called summation notation. So here comes the easy part. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and when you add all of that up together, you get a grand total of 55, and that is the answer. The answer to that problem is 55. Okay, so next one. This time we're going to start when j is 3. So we're going to do when j is 3, when j is 4, when j is 5, and then we're going to stop when j is 6. So here we go. When j is 3, we get a third. When j is 4, we get a fourth. When j is 5, we get 1/5. When j is 6, we get 1/6. So if we're going to add these together, we need a common denominator. 60. Yeah, 60. All of them can go into 60. So here we go. 1/3 turns into 20 over 60. 1/4 turns into 15 over 60. 1/5 turns into 12 over 60. And 1/6 turns into 10 over 60. So we're going to add these together. So denominator is going to be 60. Let's add the top. 20 plus 15 is 35. 35 plus 12 is 47. And 47 plus 10 is 57. Ooh, guess what? Both of those numbers are divisible by 3. We can reduce that fraction. 57 divided by 3 is 19. 60 divided by 3 is 20. So the final answer is 19 over 20. So again, we started with j is 3. Then we did when j is 4, when j is 5, and then lastly we stopped when we got to j being 6. All right, last example. This one's pretty easy, y'all. We're ending on an easy, light note. It says write each sum using sigma notation. So it doesn't tell you to find the sum. It just says write it using sigma notation. So I've got my sigma. Now you can pick any letter you want. I'm going to use a W. W for Wingard. And I'm going to start when W is 1. And I'm going to end when W is 7. So I've taken care of 1, 2, 3, 4, 5, 6, 7. And what would my equation or formula be? What's happening to all of these things? The number is being cubed. So W cubed. Done. That's all they wanted you to do, was take that and rewrite it using sigma notation. So let's take a look at the last one. I'm going to get my sigma symbol. I'm going to use M this time. And I'm going to start with a value of 3. When M is 3, 4, 5, ... When does it end? When M is 77. What would the formula be? What's happening to all of those numbers? They are all being square rooted. And so I will square root M, and there you go. All right, so that concludes 12.1. Your homework assignment is in Ren Web. If I'm not mistaken, I think in the next lesson is where we start to talk about arithmetic sequences and series. So I will talk to you guys on Monday. Bye-bye.